our next speaker is Xuan Zhang from Columbia University, and she is going to talk about bounded pitch inequalities for covering problems.
Thank you, Carla, for the introduction. So as she said, I'll be talking about bounded pitch inequalities for covering problems. So this is joint work with my advisor, Xuan Zhang, and also Professor Daniel Beanstalk. So first, let me just quickly introduce what is a covering problem. So essentially, a covering problem is the optimization problem over the set of 0, 1 points that are feasible for a set of cover-like inequalities denoted by ax greater than or equal to b. When you only have one inequalities in this sequence of inequalities, you essentially have the special case, which is called the minimum knapsack problem. And then we denote it by min nap a and b. So a is the left hand, the coefficients, and not b, beta, and beta is the right hand side. So why do we care about covering problem? I don't think I need to convince you guys anymore, but let me just quickly mention some of the reasons. So first, they appear in many applied settings, such as in capacitated network design problems and also in crew scheduling problems. They're also relevant in computational IPs. And also just theoretically, there are still many open questions regarding the structures of the feasible solutions. So in this talk, I'll be focusing on a specific class of inequalities for the covering problems. And this class is known as bounded pitch inequalities. So what exactly is pitch? So a pitch of an inequality with non-negative coefficients and also non-negative right-hand side is the minimum number pi such that the sum of the pi smallest positive entries of the coefficients is at least the right-hand side. So for example, this inequality here, I claim that it has pitch 4. And the reason is that if you take the 3 smallest positive integers, like positive coefficients, which are 1, 2, and 3, you can only sum up to 6, which is not enough for the right-hand side. But if you sum up the 4 smallest positive entries, then you have 1, 2, 3, and 3, and that will be more than 7, the right-hand side. So why do we care about bounded pitch inequalities? Essentially, there have been many works in the literature showing nice properties of them. So here I listed 2 of these results. The first one states that to approximate the CG closure of a set covering problem is actually enough to satisfy all valid inequalities of pitch that is bounded by a certain level. And this is shown by Beanstalk and Zuckerberg. They also show that for every constant pi, or for every constant, like for every pitch pi, there is an algorithm that if you're given an LP for a set covering problem that satisfies all valid inequalities of pitch less than or equal to pi, this algorithm will be able to produce a polynomial size LP that satisfies all valid inequalities with pitch less than or equal to pi plus 1. So what these 2 kind of results tell you together is that if you have an LP that satisfies all valid inequalities of pitch 1, then this algorithm, you can give LP to the algorithm, which then generate an LP that satisfies all valid inequalities of pitch less than or equal to 2. And then you can just keep on doing it until you reach a certain level, which will approximate a certain level of CG closure. So of course, besides Beanstalk and Zuckerberg, there have been many other hierarchies proposed in the literature by many different authors that essentially achieve the same results as what is showing in this theorem here. So in this talk, I'll be focusing on particular 3 topics. The first one is I want to talk about the relationship between inequalities with bounded pitch and those with bounded coefficients. And then I will give a positive result, which is a polynomial time algorithm that approximately separated over the set of bounded pitch inequalities that are valid for a minimum knapsack instance. And lastly, I will give a negative result, which is a lower bound on the extension complexity of inequalities with bounded pitch. And I will show that they grow super polynomially in the pitch. So let me start with the first one. So just by the definition of pitch, it should be pretty easy to observe that when you have a coefficient with coefficients and right-hand side bounded by pi, then the pitch is also bounded by pi. And this can be easily demonstrated by the following kind of trivial example. So here, all the coefficients are 1, which is the smallest possible integers that is there. And then if you take 5 of the ones here, you'll be exactly having 5, which is the right-hand side. And this inequality have exactly pitch 5. And then you won't be able to have a pitch that is more than 5 in this case. So if your right-hand side is 5, there's impossible to have a pitch more than 5. So a natural question to ask is that, what about the reverse? So easily you can see that bounded coefficients implies bounded pitch, but how about the other direction? If an inequality has bounded pitch, does it mean that it also has bounded coefficient? Actually, a trivial answer is no, because you can come up with like a pretty trivial examples, like I have here. You actually have a really absurdly like large coefficient here, but this inequality only has pitch 1, because you just need to take this one item to satisfy the right-hand side. So we need a better way to ask this question. So instead of focusing on all the inequalities that are out there, we chose to focus on what is called undominated inequalities. So inequality is undominated if it cannot be written as a conic combination of other inequalities of pitch less than or equal to the pitch of the inequality under consideration. And then also all these inequalities have to be valid for the min-up instance that is defined by the inequality under consideration. It's kind of convoluted definition a little bit, but it will be easily seen through the example. So the kind of absurd kind of example I talked about earlier, this inequality is actually dominated because this inequality can be written as a conic combination of 2 other inequalities, which are more normally what you see for like constraints or inequalities. And these 2 can just be easily seen through some kind of combinatorial arguments that are valid for the min-up instance that is defined by this inequality here. Right. So an updated question we can ask is the following. So if you're given an undominated inequality with bounded pitch, does that tell you that you will have bounded coefficients? And now the answer is actually not just a trivial yes or no, and it's actually more complicated than that. So it is a folklore that if for an undominated inequality with pitch 1, its coefficients can only be 0 or 1, and you will be having the following format. And it's shown in Beanstalk et al. That if this inequality have pitch 2, then its coefficients will be bounded by 2. And you'll have the format which I have here. What we show is that if the inequality have pitch 3, then the coefficient is actually bounded by 6. And then they have the following format here. So it seems to us that there is a pattern of what's happening. And we kind of hypothesize that when we go to pitch 4, then the coefficients might be some number that is like a 12 or 24. But to our surprise, what happens is actually once you get above pitch 4, the coefficients is no longer bounded. So this is a kind of interesting, cute result here. But of course, you can ask, why do we even care about this? Like, what's the point of asking this kind of question? And the reason we think about this question in the first place is because in the paper by Beanstalk et al., which I mentioned earlier, they gave a polynomial time algorithm that solves like approximate separation problem over valid inequalities with bounded coefficients for the minimum knapsack problem. And our hope was that if bounded coefficients is the same as bounded pitch, then their algorithm will just directly implies that there exists approximate separation algorithm over inequalities with bounded pitch. So although our hope was not true, we're still able to show that their algorithm indirectly implies that there is there's an approximate separation algorithm over inequalities with bounded pitch. So I think I'm kind of running out of time, so I'm not really going to go deep. I'm just going to give you a quick kind of like explanation what is approximate separation. So here you have an inequality. So in approximate separation, when you're given a point, you will like, if that point falls into the gray region, you want to be able to tell. And if the point really like violates this inequality a lot and falls into the red region, you also want to be able to tell. But if the point only slightly violates the inequality and falls in the middle, then you don't really care and you're allowed for some errors. So one thing I want to point out is that here we're really only considering like approximate separation problems and not the exact separation problem, because the exact separation problem is already NP hard if you just consider inequalities with pitch 1. So I'm not going to go too deep about like how we prove this thing, but rather I will go to the next result, which is kind of looking at pitch from a different perspective. So it's clear that as the pitch increases, the sheer quantity of inequalities will be increasing. But we're interested in that is the quality of the inequalities also increasing, or are the inequalities getting more complex? So we'll be measuring this complexity by extension complexity, which is, so let's think about this as a polytope P, and the extension complexity of P is the minimum number of facets of any extension of P. And an extension of a polytope is just a polytope lying in a higher dimensional space, which can be affine projected exactly to the original polytope P. So what we show is that there are infinitely many matrix, 0, 1 matrix A, such that if a polytope Q is a realization of the convex hull of all the 0, 1 points for that set covering instance, and this Q satisfy all the points of the Q satisfy all valid inequalities of pitch at least pi, then the extension complexity follows this. So it's super polynomial in the pitch. So I think I'm kind of running out of time. So quickly, like the proof idea is that we'll be using this famous polytope in this extension complexity community, which is the correlation polytope. And for this polytope, it is shown that if you consider a certain inequality is valid for the correlation polytope, that every single kind of polytope squeezed in between this correlation polytope and the certain inequalities will have very high extension complexity. So we simply just construct an instance of the set cover instance with like a sparse A matrix, and then have some like certain inequalities of pitch pi that can, like both of them will project exactly to the correlation polytope and the inequalities for the correlation polytope. And if this is true, then what it implies is that essentially everything kind of squeezed in between here also will have very high extension complexity. Okay. So one last slide is this is an interesting result for us, is because this is essentially the first lower bound result on bounded pitch inequalities, although there have been many other works like kind of focusing on the upper bound on bounded pitch inequalities. And then this is like the best result by Fioroni et al. And they showed that the extension complexity is polynomial in the pitch as compared to ours super polynomial in the pitch. Okay, so let me just put what I talk about in the final summary page, and thank you for your attention.